Hi folks, Chris McClure. Now we will talk about using the normal probability distribution, which is, as a reminder, a continuous distribution as a way of approximating the binomial. Now we already had the discussion of using the Poisson distribution to approximate the binomial. The Poisson is some other discrete distribution. Normal is a continuous. And this actually will turn out to be pretty easy, as I shall show you. So we're going to see how this method for using a normal distribution as an approximation to a binomial probability distribution is done. Now, you're going to see the letter n. N is the sample size. P is the probability of a single success. And Q is the probability of a single failure. P plus Q is equal to 1. And we're going to see that the condition that n times P must be at least 5, and that n times Q must also be at least 5. They have to be satisfied. Then the probabilities for a binomial probability distribution can be approximated pretty well by using a normal distribution with the mean and standard deviation of, so we will let the mean of the normal distribution to be equal to n times p, which shouldn't be surprising. In fact, it should be sorry for the pun, but expected, because the expected value for a binomially distributed random variable is also n times p. So a mu is going to be np. Sigma, the standard deviation for your normal distribution, will be the square root of n times p times q. Remember that q is 1 minus p. And we'll do an example here toward the end of this presentation. Now here's a review. Binomial probability distribution. We need to have a fixed number of trials. The trials must be independent. Each trial must have, one of two possible outcomes, either a heads or tails, for example, or you draw a card that's either black or red, etc. The probability of success remains the same in all trials. That goes along with the idea that the trials must be independent of each other. And I showed you in the presentation for that section how to calculate your binomial probabilities by hand and technology. There's also a table A-1 in which you could look up those binomial probabilities. I wouldn't do that unless you don't have technology at your fingertips, as in, like, for example, a calculator. Use your graphic calculator. Approximation of the binomial distribution with a normal distribution, we're going to require that np and nq are both at least 5. We're going to let mu be equal to npq, or sigma is equal to square root of npq. And the random variable has a normal distribution. Okay, here's the procedure for using the normal distribution to approximate a binomial. Verify that np and nq are at least 5. Calculate mu and sigma as we indicated. Identify the discrete whole number x that is relevant to the binomial probability problem. Focus on this value temporarily. Before we go any further, let me just tell you the whole reason that we would use the normal probability distribution to approximate the binomial is when the sample size is so large that a handheld calculator like the TI-84 might choke and not be able to handle the probability calculations. Okay, or even if it could, it might take a while. It might just be easier to convert over to the normal and look up a normal probability, which is actually pretty easy to do. Here's how we would do this by hand. Do steps 1, 2, and 3, as we indicated. Then step 4, draw a normal distribution curve centered at mu. Draw a vertical strip centered over whatever x is. X is going to be the number of successes. And that vertical strip is going to be where you take half a unit below and half a unit above. It's a vertical strip, and I'll show you an example here in a minute. It looks something like this. So here's a vertical strip centered at 235, half a unit below, half a unit above. And you just want to highlight that. Determine whether the value of x itself is included in the probability calculation. And if it is, then you will include it by including that whole strip. But if your probability calculation is strictly a greater than or a less than, then you will not include that strip, as we shall see in our example here. Finally, using either x minus 0.5 or x plus 0.5 in place of x, find the area of the shaded region. Find the z-score associated with x minus 0.5 or x plus 0.5. And then if it's area to the left, then you know what to do. Just look up that area or calculate it on your graphing calculator. If it's area to the right, then find the area to the left and subtract from 1. So let's take a look at our example here. Now, for the American game of football, when you get to the end of fourth quarter and the game is tied, then it's going to go into overtime. Now, which team gets to choose whether to kick or receive is dependent on a coin toss. Now, some people have claimed that the coin toss is not fair. Let's go ahead and read this example here. In 431 NFL football games that went into overtime, the teams that won the coin toss went on to win 235 of those games. So the question is, does winning the coin toss give an unfair advantage? Well, we're going to test the claim that it is unfair. Now, if the coin toss method were fair, teams winning the coin toss would win about 50% of the games. Now, half of 431 is 215.5. Now, is the 235 games that were actually won by the winning, or by the team that won the coin toss, is 235 such a departure from 215.5 as to be remarkable? Well, we shall see. Now, let's go ahead and assume, under the assumption that the coin toss is fair, meaning that, let's just temporarily assume that the coin toss does not confer a benefit, does not confer an advantage. And with that assumption goes the assumption that there's a 1/2 probability that the team that wins the coin toss would win the game. So under this assumption, find the probability of getting at least 235 winning games. At least. That means 235 or more winning games out of the 431 played. You'll see we do this sort of testing when we do hypothesis testing. Now, the given problem assumes a binomial distribution with 431 games played, so n is 431. N is the sample size, right? So 431. And an assumed probability of success of P is equal to 0.5. So that means Q is also equal to 0.5. So we're going to check our conditions here. NP is 431 times 0.5 is 215.5. That's certainly greater than that's greater than 5. Greater than or equal to 5. NQ is also greater than or equal to 5. We calculate mu, which is equal to NP, which is 215.5. Sigma, square root of NPQ, that works out to be 10.38027. So we're going to use this value of mu equals 215.5, and this value of sigma equals 10.38027 as our mean and standard deviation for the normal distribution, which approximates the binomial. We want the probability of at least 235 wins, so x is equal to 235. And because we say the word at least, that means that we're going to include 235. That means we're going to back it off by half a unit. So we're going to include 235 by including the strip that goes from 234.5 to 235.5. If it was greater than 235, then we would have our calculation go from 235.5. But because it's at least, that includes 235, we'll go from 234.5 to 235.5 and beyond. Here's that shading that I showed you earlier. Here's a normal distribution with a mean of 215.5 and sigma being equal to 10.38027. And then here's 235, which is about 2 standard deviations above the mean. We backed it off and put it forward by half a unit to give the strip. But we want to find this area to the right of 235. And when we're doing the normal approximation to a discrete distribution, we have to do this correction by backing it off, or going by half a unit before or after. Again, we're going to go from 234.5 to the right because we're including 235. Now, so what is the area under the curve to the right of 234.5? Now, 234.5 is 1.83 standard deviations above the mean, as you can see from this calculation. And what is the area under the standard normal curve to the right of 1.83 standard deviations to the mean, from the mean to the right? And that probability works out to be 0.0336. So if you're not sure, I'll show you how to calculate that. Let me go into my folder here, and I'll pull up the z-table. There's my z-table. $1.83. Well, we want the area to the right. Using our z-table, we'll look up the area to the left, and then we'll subtract from 1. So here z is equal to 1.8, and then we will move over to the 0.00, 0.01, 02, 03. So this number right here, the 0.9664, is the area under the curve to the left of 1.83. Well, 1 minus this 0.9664 will give us our probability, meaning the area under the curve to the right. And 1 minus 0.9664 is 0.0336. I'm going to pull out my graphing calculator here. I'll show you how to use your graphing calculator to do this. TI-84 if you happen to have one. I realize not everybody does, and that's fine. Go into your distribution menu, and we'll go down to option 2, which is normal CDF. Now, If we don't care about standardizing this, then we can calculate the area under the curve of 234.5. So 234.5 is the left endpoint, comma. The right endpoint would be positive infinity, which is 1 EE 99, comma. Now this is for a normal distribution with a mean of 215.5. So we'll do 215.5, comma, standard deviation of 10.38027. 10.38027, close parentheses. And we'll hit enter. And we get 0.0336 approximately as our probability. And that goes along, that matches the calculation that we made from the table. Now, let's just verify that this is actually a pretty good approximation to the binomial. So we can go back into the distribution menu and actually do the binomial calculation, or at least try to. So we're going to, within the distribution menu, go down to binomial CDF. Sample size was 431, comma, probability of success was 0.5. That's our that's our little p-value, not to get mixed up with our p-values from hypothesis testing, which we'll talk about some other time. And then the number of successes. Now, because of the fact that this is going to go count up the probabilities for from 0 to 1 to 2 to 3 to 4 to ... up to whatever number we tell them, because after all, this binomial CDF cumulative, we want it to go up to 1 less than 235. So we'll do 234. And we'll do close parentheses. Now, before I hit enter, if we did this right, syntax-wise, the computer is going to calculate the probability of having either 0 wins, or 1 win, 2 wins, or 3, or 4, or 5, or 6, or 7, or ... or 234 wins. Meaning this will calculate the probability, the binomial probability of having fewer than 235. And then we'll subtract from 1 to calculate the probability of having at least 235. All right, so I'm going to hit enter and see what happens. And then we'll do 1 minus that answer. And notice that our binomial probability is very close. This is the actual real probability, or the normal probability is very close to the binomial probability. Now, 431 is a relatively small sample size, but if it were 40,000 for the sample size, then the graphing calculator would choke on it. But again, you can switch over to the normal approximation. You'll have a very good approximation. Okay? So get to know how to do the normal approximation to the binomial. All the details are in your textbook, and you'll do some examples in the homework. And like I had mentioned earlier, the reason that we subtract 0.5 or add 0.5 is because of that so-called continuity correction. That's the issue that we have to deal with whenever we use a a continuous distribution to approximate a discrete distribution. Okay. So this right here is just going to tell us exactly how the continuity correction works. If we wanted to calculate the probability of having at least 235 successes, then when we use the normal distribution to approximate, then we'll calculate the area under the curve to the right of 234.5 because we want to include 235. But if the event is more than 235, then we will find the area under the curve to the right of 235.5. If we see the word at most, that includes 235. That means less than or equal to 235. So when we use the normal approximation, we will find the area to the left of 235.5. Again, to make sure that we include 235 in that narrow strip of 235 plus or minus 0.5, right? Fewer than 235, that means that we don't include 235, so we'll find the area under the curve to the left of 234.5. If we want to calculate the area of having exactly 235 successes, then we will find the area under the curve between 234.5 and 235.5 exactly. Remember, for continuous distributions, the probability that your random variable x equals any particular number is 0. The only way to get non-zero probability is to find the area that x ranges over some interval. In this case, the interval will be 1 unit long, half a unit below and half a unit above. Okay, folks, well, we'll leave it there for now. And next time we're going to push into Chapter 7. Okay? Have a good day. Have a good weekend. I'll record some more videos over the weekend. I'm going to be on vacation next week, by the way. But I'll make sure that you have videos to get you through Chapter 8 while I'm gone. Okay? So starting with Chapter 7 next time. Okay, folks. Have a good day.